Hi, I'm David Kohlbrenner. This is work with my advisor, Hovav Shacham at UC San Diego. And it's titled, this slightly awkward, On the Effectiveness of Mitigations Against Floating Point Timing Channels. It could just as easily have been titled something like, How Effective Are Mitigations Against Floating Point Timing Channels? And the answer to that question is not super great. So these are 3 CVEs that were landed as a result of this paper on desktop browsers. And all 3 of them are pixel stealing attacks on web browsers using floating point side channels. Now, there's a lot of hyphens in that sentence, so we have to talk about a couple different topics today. We're going to start with talking about pixel stealing attacks. What are they? We're going to go through floating point performance benchmarking to understand how we can leverage it in pixel stealing attacks. We'll then show how to do that. And then we'll go through beating defensive schemes against floating point timing side channels. So let's start with a little bit of background on pixel stealing attacks themselves. So pixel stealing attacks really got their start with Paul Stone's excellent pixel perfect timing attacks on HTML5. And in these attacks, you have 3 actors. You have an attacker who hosts a web page. You have a victim who visits said web page and is logged into the target, which is the 3rd actor. And the 3rd actor is some target web page that hosts visual private information about the user. And the impact of these attacks is that the attacking web page is able to derive this visual secret information about the user that exists on the target web page. You could think of this as the login status or username in kind of the more benign case of the user, or it could be something that is kind of more impactful depending on the website. And all of these attacks, again, starting with Paul Stone's work and including some work that our group has done previously, follows this kind of same pattern. We start with an attacker web page that creates an iframe of the target web page. This is when the user visits the page, visits the attacker's page. The attacking page then, through a stack of browser-specific and incredibly ugly CSS and HTML, isolates an individual pixel that they want to read from this target iframe. They then expand this pixel using, again, a stack of pretty ugly CSS, HTML, and other transformations. And they get many, many copies of this target pixel. And this is because we're going to be running a measurement over these pixels, and we need multiple data points. We then run an SVG filter over the multiplied pixel. Now, SVG filters are a feature that your browser supports. They let you do everything from clipping and skewing arbitrary DOM elements to applying complex lighting models with shading to arbitrary DOM elements. Turns out we don't actually care at all about what the rendering of this SVG filter looks like. What we care about is how long this SVG filter takes to render. And based on how long it takes to render, we can classify that original target pixel as either white or black. And to do this, we use the high-precision timing interfaces that are built into all modern browsers. They let us access the timers necessary to do these attacks. And if you want this to work, you obviously need a timing difference in the SVG filter based on what the original pixel value was. So in Paul Stone's original work, they used the FE morphology filter, which had a code fast path. If you just read the C++ implementation in Firefox, there was a fast path and a slow path. They were able to abuse that as a timing side channel. In work that our group has done previously, we were able to leverage timing differences in floating point computation in hardware to leverage these attacks. So if we want to do that, we need to know something about how floating point performance works. So this is an IEEE 754 single precision floating point format. It's a 32-bit format. You know them as float, maybe. There's also double, which is a 64-bit format. You may be familiar with that as well, and I'll mention it several times. And in this format, we have an assign bit, 8 bits of exponent, 23 bits of significand, and the value is represented by the following equation. Now you'll notice I say 23 plus 1 bits for the significand. And that's because in the normal case, that is a literal normal subnormal value, or a literal normal floating point value, one that has an exponent that has at least one 1-bit in it, which is most values, the significand gets an implicit leading 1 bit on the front. So 23 plus 1 bits. Now, if the exponent is all 0 bits, we have what's called a subnormal or denormal value. And in this case, the significand gets an implicit leading 0 bit. And this is true for both single and double precision floating point. Now, if you do the value calculation for a subnormal value, you will quickly notice that the maximum subnormal value is smaller than the Planck length in meters. And in fact, most of the values down in this range are relatively useless. Computing down in this range in floating point leads to massive precision errors. You don't really get the computations that you want to occur. It is there for a bunch of very nice numeric properties that we talk about in our paper. There's good reason to have it. But because of this, it is not the default case in the hardware. The FPU, the floating point unit in your processor, doesn't really appreciate having subnormals running around, and things go really, really slowly. Now, this is well understood, well known. We leveraged this previously. Hardware designers know this. Game engine designers are very well aware of this. Subnormal's bad, subnormal's slow. And this is what we used previously. This, however, was an imperfect understanding of floating point performance. And one of the things that we do a lot in this paper is we show detailed, extensive benchmarking of real-world floating point performance on hardware. So this is a table of cycle count, of average cycle count for some particular operation given a pair of operands. And I'm going to show you several like this throughout the paper, so I'll walk through it. On the top in this one, since this is division, we have the divisor, and on the side we have the dividend. And then each cell indicates the average number of cycles it took to perform that particular computation. So it took about 12 cycles on average. White cells are cells that are the median value across all operand values. So most operations you would expect to take about 12 cycles. Now, previous work has leveraged essentially this column. This is the double precision subnormal values, essentially. They run about 60 times slower than the median case. They're very easy to detect if you're running a timing attack. But what we missed kind of initially was there's actually classes of values that run faster than normal. There's a whole bunch that run in about 6 cycles. And if you start to break it down what value types do this, they are powers of 2 and 0. And if you think back to the floating point format, it's got a significand and an exponent. Powers of 2 and 0 have a 0 significand, not exponent. Exponent deals with the subnormal versus normal. And if you were to build hardware that operates on a value type that has 2 discrete parts, and if one of them is all 0 and you run in half the time, you can make some guesses about what their hardware is doing. We don't know for sure, but we have some educated guesses. But possibly the most interesting thing that we found were these values. It turns out that there are strange, analog, kind of complicated combinations of timing effects that occur in floating point land. There's a couple cases here where we have 150 cycles. All of these are very dependable timings. There's one where we have 175, and we have some actually really good guesses as to why it's 175. It's not worth going into them at the moment, though. So kind of the high level here was subnormals are slow. We knew that. Lots of people were aware of that. We were able to use that previously. But there's a more nuanced understanding that as security engineers we should be aware of. And this is a summary table demonstrating the different effects that we saw on the on one of the Intel platforms that we tested, and both for single precision and double precision. The general high-level story here is division is scary and dangerous. Square root is really scary and dangerous. Addition and subtraction are usually fine. So OK, we've got timing differences with floating point. How can we leverage these to build floating point timing attacks in pixel stealing? So if you remember, in the pixel stealing attack, we need a timing difference in the SVG filter. It should not surprise you at this point to learn that SVG filters run floating point math. So we're able to use those timing differences that we just saw to run SVG filter timing attacks. And the previous attack that we used and the filter that we continue to use in a number of cases in this work is the FE convolve matrix filter. It's a very straightforward filter. It has an attacker-defined kernel, and we're going to essentially multiply that kernel just across the input pixel repeatedly. So we're going to get a whole bunch of multiplies here that are going to be attacker-controlled on one end and secret on the other. And that's exactly what we want if we want to leverage these floating point timing differences. And this exact attack in kind of its most naive form worked great for us in Firefox 23 to 27. We are on Firefox 50-something, so things have changed a little bit. So how do we pixel steal on major current browsers? Now, the objective here is not just to land some fun bugs. It's also to try and motivate changes in browser architecture to mitigate and or remove this attack surface. So we're going to start with Safari because it's the most boring attack. Safari had not made any particular major changes to their graphics rendering stack since our previous work, so we can still use their FE convolve matrix implementation. It's still relatively vulnerable. We just need to kind of rebuild this horrific stack of transformations and targeting that we do internally. Notably, we actually have to change the way that we count how long it takes for the frame to render. And this actually ended up being the most stable of our attacks. I'm not entirely sure what's happening down in the deep depths of Safari's rendering stack, but their frames arrive at extremely dependable times with very little variation, and that makes our attack run gloriously smoothly and very dependably, which was great. Now, I told you that Firefox stopped working in version 28 with our previous version, and that is because Firefox, independent actually of our suggestion, started pushing their SVG filters to a fixed point implementation. That is an implementation that does its non-integer math on the integer unit rather than on the floating point unit. And since they're not using the floating point unit anymore, we obviously can't run a floating point timing attack. That's OK. They haven't ported everything yet. So we dug through the implementations of many, many different filters. And what we found was that one of the complex lighting filters still had what we were looking for. So if you actually look at this code, this is inside of the core loop for the lighting rendering. This is what we were looking for, a division with a floating point value. And it gets better because that is an attacker-controlled value, and that is a secret value. And so that line by itself buys us yet another one of these floating point timing attacks. Chrome, however, was probably the most interesting one. So Chrome has attempted to disable subnormal performance impacts entirely using a combination of FPU State Flags, which are the flush to 0, or FTZ flag, and the denormals R0, or DAS flag. The combination of these flags should remove all impact of subnormal floating point values. Now, FPU State Flags are a nightmare to manage. They are a piece of global hardware state. You need to make sure that no libraries that you load during runtime are touching your FPU state, because they can. You need to restore your state if you're a good FPU citizen every time you use it. You can do this, but it's going to be annoying. And worse is it's not actually as effective as we would like it to be. So this is what happens when you run the exact same division tests we saw before, but with the FTZ and DAS flags enabled. And what you see is that our special value classes of powers of 2 and 0 are still running at about half the time. And somewhat amusingly, subnormals now run fast. And that's because the denormals R0 flag is operating as expected and causing them to be treated as zeros. So we, in fact, still get performance impacts, although in the other direction, from subnormal floating point. But that's double precision. Chrome doesn't use double precision, so they should be pretty safe. In fact, single precision division was, on our test platforms, completely stable. There was no timing variation that we could detect. But square root, I said, is really nasty. And single precision square root does still show timing variation. In fact, it still shows that same variation on powers of 2 and zeros. The good news for Chrome, as far as we can tell from reading far too much of their implementation code, they do not use division in a dangerous way. They do not use square root in a dangerous way. They only ever use it on attacker-controlled values and never on secret values. So how do we beat their implementation? I told you FPU state flags were a nightmare to manage. They're a nightmare to manage. There's a weird case where when Chrome is attempting to render its filters on the GPU and has to cancel that, they don't properly set FPU state flags. The way this works, in general, is approximately this flowchart. In the average case, if we shove a filter into Chrome, what it does is it does not render on the GPU by default. Most filters do not prefer the GPU, and so we render on the FPU, on the processor itself. And this sets properly the FTZ and DAS flags. However, we want to cause this GPU failure case that I was talking about earlier. So what we're going to do is we're going to first choose a filter that prefers the GPU. And the filter we're choosing there, in this particular case, is a 3D rotation of the DOM element. This causes it to prefer GPU execution. So now we're executing on the GPU. But if we just put our FE convolve matrix back through, now we have a problem, which is we're still rendering on the GPU because the filter has a GPU implementation. If you read the code very closely, however, you discover that some filters have additional checks. Notably, the FE convolve matrix filter has a bail condition if the filter is too large, if the kernel matrix is too big. So what we do is we abuse that. And in that case, at this point, it should be clear, they don't set the FTZ and DAS flags correctly. So that's Chrome. Now, last year at USENIX, there was a new defensive scheme proposed against floating point timing side channels called EScort. We were incredibly excited when we first saw this announcement because this is defensive work in kind of the attack space I like to work in. So we started digging into it. And this is a hardware-based approach that relies on SIMD instructions, or single instruction, multiple data operations. And these operations allow you to perform multiple computations, so multiple multiplies or multiple divides, all at once using extra large registers, and you squeeze the value operands into them. And the hope here was that we were going to be able to obscure the runtime of the real floating point operation, so it wouldn't be this fast case or slow case. And we'd be able to do that by constructing a dummy operation and escorting it through the SIMD instruction. So the slow case would always occur. The program would always see the slow case occurring since everything occurs all at once. And this works if these operations run in parallel. So we got a hold of the code with some work with the authors, and we benchmarked it. And it didn't come up quite as we hoped. The good news here is that we are seeing less variation than we were before. Notably, the timing variation we're seeing here is about 5% rather than 60x. And as someone who writes these timing attacks, I can tell you that a 5% difference is going to be a nightmare to detect, even if it is stable. But again, we're still seeing this timing variation based on powers of 2 and on zeros. This is for double precision and division. The good news for multiplication is that double precision multiplication actually looks pretty safe. EScort does manage to beat up some value types. And in fact, this is the summary table, again, compared with what we saw in the default case for what our benchmarking on EScort saw. So you might say, OK, we can be careful about what operations we use. We can use add, subtract, multiply, and we can be careful about div and square root. When you start benchmarking older or more esoteric processors, that starts looking a little less promising. On AMD, we saw slow add and subtract operations for some reason. We're not entirely sure why that happens. But that means you're now limited to safe multiplies, which is really not enough for implementing complex floating point math. So what we were hoping to see was something like this, where we would get this parallel operation and we'd be able to obscure the running time. What we're actually seeing looks really close to sequential execution. And if you dig into all of our data and you look at our, we also did some work with performance counters to measure execution here. Everything's bailing out to microcode in the CPU. And as far as we're aware, the microcode that executes this cannot perform these operations in parallel. It has to perform them sequentially. We talked to Intel about this. They were totally uninterested in telling us what their microcode does internally, unsurprisingly. So EScort has some potential. It definitely fixes a couple cases, but it's extremely platform and value type specific. Now, I told you about attacks on browsers a second ago. I told you I walked you through some bugs. I wouldn't get to walk you through bugs unless there were fixes deployed. So Firefox fixed this in Firefox 52. They issued a patch very rapidly that just restricts the value range of the attacker-controlled value we were abusing. This removes the ability to use that particular avenue to attack Firefox. And as far as we're aware, they're continuing to port their filters to fixed point implementations to slowly remove these channels as well. Chrome, in Chrome 60, simply made sure that the scoping for their FTZ and DAS flags properly includes this GPU bailing case. As a side note, they discovered while fixing this bug that the FTZ and DAS flags had never been set on any Windows build. So yet again, managing FPU state, not a pleasant experience. But the most exciting fix comes from the least interesting attack. And that is that Safari has removed the ability to run cross-origin SVG filters. So I can't run any of my attacks on Safari anymore to steal cross-origin pixels. It doesn't matter what their implementations look like. This was actually a really notable engineering effort. Along these lines, going forward, if you're a browser vendor and you work anywhere near the graphics stack, I would love to evangelize removing cross-origin SVG filters to you. They shouldn't be there. They let you compute over foreign pixel data with attacker-controlled values. Fixed point, if you need to do if you need to do non-integer math, still looks like a really promising candidate. Previously, we actually released a fixed time, fixed point math library, and last year at USENIX, another group proved it could be constant time, which is really neat. You might say, okay, well, maybe we just shouldn't be using these wacky Intel processors with their strange floating point performance. We can use GPUs or ARM or AMD processors. GPUs look like this. It's not super pretty either. On this slide, I see a 5x slowdown in some cases. So I would not rely on those to not have performance slowdowns based on subnormals. And I told you before that addition on AMD, specifically a couple of old AMD phenoms that we tested, showed notable slowdowns up to pretty significant, 216 cycles versus 7. So if you want to deal with non-integer math and you want to do so safely, there's a lot you need to worry about, and you need to be extremely careful about your platform, your value types, and what your defensive schemes guarantees are. With that, I will go to questions, and tools to do your own benchmarking, as well as results for all of the processors we have benchmarked previously, are available on this website.
Steve Checkaway, University of Illinois at Chicago. Great presentation. One question I have is, your work seems to rely on browsers having high precision timers that are exposed to the attacker. Is that actually a reasonable thing to do, or should browsers expose much worse timers?
They should not expose high resolution timers. Actually, so yes, they should not be exposing high resolution timers. However, that is unfortunately a lost cause. A recent implementation that is being pushed out to all major browsers includes full shared memory access for JavaScript. With the advent of shared memory in JavaScript, we actually now have more accurate timers than the high precision timers that are available previously. If you're a browser vendor, don't add shared memory to JavaScript, even though it's too late.
Great, thanks.
Hi, Daniel Genkin, UPenn UMD. Anything known about integer units in terms of timing deviation?
So division on all Intel processors is well known to be timing variable based on operand values. I've spent far too many CPU hours trying to find other timing variations that are dependable, and I don't have any right now for you on integer units. They look pretty safe. Intel is unwilling to commit to that.
Hi, David. Thanks for your paper and thanks for your presentation as well. I had a quick question. You briefly alluded that with the 5% variation, it becomes harder to launch the attack. And I guess part of the difficulty is that you have to repeat the attack multiple number of times to amplify it. Could you give a ballpark estimate of how much did you have to amplify it by compared to, let's say, a baseline attack?
It depends entirely on how stable. So the question was essentially how much can we abuse that 5% difference we saw in EScort versus kind of the 600% differences we were seeing previously. So it depends entirely on how stable that timing difference and your timers are. So for example, if I were running on Safari, I would actually be a lot more convinced I could measure that 5% difference just based on the benchmarks that I've seen. On both Firefox and Chrome, there's enough noise that I get just out of the measurements in general that I would not expect to be able to hit that 5% difference on EScort without being able to do really significant pixel multiplication, and there are actually some architectural challenges beyond a certain level.
Nice. Okay, thanks.
Hey, Connor Bolton, University of Michigan. So I just had one quick question, which was you mentioned that the 5% makes everything pretty difficult. How much and you looked at other processors as well, how much does the variation in processor affect the attack? In other words, do you have to know the processor that you're attacking to be able to make the attack work?
No, you do not. So in all of our pixel stealing attacks, we have a learning phase that runs first, where it uses known black and white image data, and it's able to establish timing thresholds to do all of that. So we've run that attack on every processor that we've tested, and it's been fine.
Thank you.
I want to ask, are the benchmarks between different processor types are the same or not? Because you only give the figures about your...
Yeah, the differences that we see, like what cells would be colored blue, orange, or white, tends to be relatively the same in a processor family. So if you're looking at relatively recent Intel processors, they're all going to have kind of the same shape of performance, but their actual numbers are going to be different. Our website actually has a bunch of different Intel processors benchmarked, and you can look at tables for all the different operations that we have on those processors. And if you want to run some of your own and then hand them back to us, we can also put them up there.
Are any of these attacks or similar attacks applicable to mobile?
So that's a good question. We have not looked in detail at ARM's floating point implementations. Kind of a naive run of our attacks on mobile browsers has been ineffective. It's going to require some more diving into the hardware performance aspects of individual ARM processors that we just haven't had the chance to benchmark.
Okay, thank you.
So some of the Intel processors have pipelined floating point unit, and some of them have non-pipelined. The experiments that you ran, does it make a difference?
So I do not remember if any of the processors we looked at have a non-pipelined FPU. I believe they all had a pipelined FPU. I'm not 100% sure because that was not something we were differentiating on when we were doing our tests. So we didn't kind of write that down. I don't think we would see a significant difference in the attack's capabilities because the loops that we target in the real world, like in the actual attacks, not just the benchmarking, are loops that perform some floating point computations and usually a couple other things, some memory stores. So the pipeline's going to be in use there, but it's not going to be just kind of a slammed full pipeline that we're measuring, if that makes any sense.
So, following up on that question, I think Intel Atom processors use non-pipeline floating point unit. Okay. For the pipeline units, the sequence in which you send the operations will make a difference, yes. Right? So have you explored that?
No. So, I mean, again, we've been focused primarily on steady state throughput of individual operations for our benchmarking, and then for the attacks, we find tight loops that are pretty close to that. That's stuff we would love to also look at benchmarking and looking into this space. We just haven't gotten there.
Thanks.
Let's thank the speaker again.